Welcome, everyone. This is our monthly LGU forum, and our agenda today, we're talking about the future of flood mapping, and we'll be starting with me and Jeff Weiss talking about 2D modeling and some challenges with 2D modeling in terms of regulations. And then Jeff's going to talk more about the future of the flood risk data, and Jeff and Gary will be talking about Stantec's flood predictor tool, something that we got a little pilot done of that and are deciding how we'll use that, in what ways it'll be useful.
So good morning, everybody. My name is Jeff Weiss. Like Ceil said, I work with Ceil and Gary in the floodplain group. I'm going to lead off here talking about 2D modeling and kick it over to Ceil to talk about the regulations. In some of your communities, you may have already started seeing some 2D modeling. Some folks may have not seen it yet. So just to give a quick overview of kind of the differences between what we call 1D modeling versus 2D modeling. I'm going to show a couple of slides here to try to make sure everyone's on the same page here. Traditional modeling that's been going on since the late 70s is usually what we call 1D modeling, and it's 1D because it only goes one direction. It only flows downhill along the stream. So in a typical model, you might have cross sections cutting across the stream, and we're able to pull elevations on the cross sections from LiDAR, or back in the day it used to be from USGS topo maps, and then the model just computes the water surface elevation. You plug in a flow and it computes the water surface elevation as the water goes from cross section to cross section down the stream. So you have to put in information like bridges, and you have to put in a lot of judgment calls on where flow can and can't go. It still works pretty well, but there's a lot of judgment that goes into it, and it's limited because, like I said before, water can only go one direction. It can only go from one cross section to the next. But I'm sure many people have situations in their communities where they know water goes in one spot. Water might go two different directions, depending on conditions on the ground. 2D modeling has been around for a while, but the last handful of years, it's really taken off. I mean, the computing power has gotten a lot better, and available topo and LiDAR around the state has gotten a lot better, which makes 2D modeling a lot easier. So with the 2D modeling, you're able to have a unique water surface elevation in every cell, versus in 1D modeling, you just have the water surface elevation right at that cross section. And then when you have complicated situations like levees, breakout flows, other complex flow scenarios, then that water is able to go multiple different directions, and the model is able to figure out how much water goes in different directions. And you're able to figure this all out with fewer judgment-based inputs, which is pretty great. So an example of a situation where we changed the situation from a 1D model to a 2D model, we did this just a couple of years ago in Northwest Minnesota. The effective FEMA maps were showing what's on the left side, where you can see the traditional 1D cross sections cutting through here. And based on the way the modeling was done, water would, we knew up here water was spilling out and going other directions, but the model wasn't sophisticated enough to figure out how much water is going to the north and west, and how much water was continuing going to the south. And the resultant map was what looked like on the left side, and this little tiny town was being shown as entirely in the mapped floodplain. Didn't take a lot to figure out that wasn't really accurate. So we changed it to be a 2D model, and the resultant floodplain looked a lot more like what's on the right side. So this is a situation where that 2D modeling provided much more accurate results. And so, to provide a little more example here, again, the 1D modeling, this is a typical cross section that was coming out of here. Again, knew some water was spilling out over onto the right side, but the model, again, wasn't sophisticated enough to figure out exactly what that was going to be. Whereas the 2D model, we were able to put in a terrain-based mesh, a LiDAR-based mesh, and put rainfall directly on it to compute the flows and figure out where the water was going. Other situations, like old maps in Duluth, many of you remember the huge storm in Duluth in 2012. The old floodplain maps in St. Louis County and Duluth look like what was on the left side, a narrow floodplain cutting through the neighborhoods. But The reality was when that flood hit, lots of water flowed down the streets, and it made lots of sense to residents that was happening, but the floodplain maps didn't show that happening in Duluth. Whereas with the newer floodplain maps in Duluth, these it's showing water going down the streets, and they're able to do that because it's done. Some of these areas flowing through the streets is done in 2D models. So that's really helped improve the accuracy of the floodplain maps in St. Louis County. And those are only in Duluth specifically, but it's not the whole county itself. So lots of areas in Duluth do have these 2D models. And one other thing that's new in St. Louis County is we have our first coastal zone being mapped. There was a coastal study done for all of Lake Superior, and so far within Minnesota, it's only been mapped within St. Louis County. So that's a new flood zone that some folks may be dealing with in Duluth. Like I said before, many communities may have already been dealing with some 2D models at the local level based on local projects. We're starting to get some 2D models being regulatory around the state. So this slide shows kind of a snapshot of where there's some of these FEMA-based 2D models that are available or will be available around the state. These orange dots show where there are a few or a handful of regulatory models that are effective. The yellow dots show where there are 2D models in the works, and they will be regulatory in the future. And then these gray dots, the blue watersheds along the southern border, and these brown, I'll stop there. The gray dots and the blue watersheds along the border, those are some watershed-based base level engineering BLE models that are available that can be used, that may be the best available data in some of those areas. So those models are available. And we'll get into a little bit later about how to determine if something is the best available or not. And then the brown watersheds up in the arrowhead are 2D models that are in the works. FEMA's contractor is working through a study to develop 2D models for these 4 Huc 8 watersheds in the arrowhead. And to give an example of kind of how some of this may work, and this is where the animation would have been really helpful. If I had that on the screen here, but if I just move this, you can see, like on a regulatory map, you can see how you might just have a floodplain along the main stem of the river, and that's fine and dandy. It gives you that floodplain along that main stem of the river, but these 2D models will give you that floodplain on the main stem of the river, but it'll also give you information on all the tributaries that come into it as well. These tributaries may not be mapped for a regulatory purpose, but it's still really valuable information that communities can use to help understand flood risk for helping site development or critical infrastructure, because not all these tributaries are mapped on FEMA floodplains. So now we start getting into some of the regulatory issues here. So first, I'm going to talk a little bit about how to determine if a model is the best available data. Then I'll kick it over to Ceil to talk more about BFEs and a couple other questions. So typically, if it's a zone AE area, meaning it's a detailed study area on your maps, it has both the 100-year and the 500-year floodplain and a floodway through there. Doesn't always have a floodway, but usually does. The best available data is usually that effective model. Sometimes a newer model may be considered better data, but it's usually that effective model, even if that's an old model from the 80s or something like that. So anyway, those effective models are pretty important in those detailed study areas. But in the zone A areas, the approximate study areas, there's a little bit of uncertainty about which model may be the best available. And the short story is, the floodplain unit staff is always willing to help make the judgment call, what's the best available data. I'll show a couple examples of that in the next couple of slides. And then lastly, in unmapped areas, there may be any model. Sometimes there's just no model available at all. So any model is best available because it may be the only model available. And again, we'll be happy to help determine if it's useful, but if it's the only model available, it is kind of up to the local folks to determine if it's a useful model for that area, if maybe the developer or consultant might need to be considering something else, or a brand new model. So a couple of examples where the 2D model may or may not be the best available. There's some old 1D models that were really quick and dirty models. In fact, they were referred to as rapid floodplain delineation models, and they were rapid, and they got a delineation, but the models aren't particularly great. In most of these situations, it's a safe assumption that the 2D model may be the best available data, or maybe the better data, even though the old rapid floodplain delineation model was used to create the Zone A models. But in other situations, for example, there's a project that the floodplain staff is working on in Rock County, and that's where the screen on the screenshot from the left is from. We put a lot of effort into that 1D model, and it's a pretty good one-dimensional model. The 2D model, there's a 2D model that covers that area, and I happen to know that that 2D model was not done to the same level of detail that the 1D model was in that scenario, in that situation. So we put a lot of information in. I used a screenshot to show how much information we put in for the bridges. You know, this was something where there's a main bridge span here on the left side, but there's also multiple culverts across the floodplain here. Usually in the large watershed-wide 2D models, they're not getting into that granular level of detail to put in all that information on these bridges. And we put a lot of information to make sure we understood how water was moving in and over this bridge. So in this situation, our judgment call would probably be such that the 1D model is the better data to use compared to the 2D model. So, and again, short story is we'll be happy to help determine what's best available for a given situation you might be dealing with. And here's where I think I kick it back to Ceil.
I'll take over. I'm going to talk a little bit more about determining BFEs. And while Jeff was explaining how the 2D modeling is more accurate, it gives a better idea of what's really happening in terms of the risk. It does get messy when we start looking at trying to figure out what BFEs are. And so I'll be going through a few examples. And this is just an old picture I had of my son and another kid looking messy. And when I think of messy situations, this picture just came to mind. I couldn't resist using that. So moving on, some of our past use of 2D types of modeling are in the metro area. We've got some of the watersheds that did use 2D modeling, swim models there. And in those cases, we were showing areas that needed to be saved as storage were shown as administrative floodway, so that when alterations were made there, that we were looking at the right modeling and making sure that any work happening in that area wasn't taking away that storage that was assumed in the modeling. But now we're getting into a lot of other kinds of situations. Jeff showed this Nashua example, and you look at it, and Jeff explained how this compares to what we had in some earlier mapping. It is much more accurate, but it's a little scary if you're the regulator, if you're the person making the decisions on whether what permits needed and what the BFE is, the base flood elevation is here. Because if you look at FEMA's viewer, there's nothing to help you here. And we can zoom in a little bit and say we're interested in trying to figure out the BFE for something in this area. We don't have it on the FEMA viewer. But if we go to the DNR's lake and flood elevations online, we do have the supporting cross sections here. And so we can zoom in and look at the area we're interested in. And in this example here, even if we take the upstream cross section, it's only a few tenths higher than the next cross section. So it's, in this example, it's not so difficult to figure out that base flood elevation. And then to get our regulatory flood protection elevation, we'll add our foot of freeboard and our half a foot for water courses for the stage increase where we don't have a calculated stage increase. But getting back to Duluth, that's one of the other newer effective map areas where we've got a lot of the 2D modeling. Things are definitely more complicated in Duluth. So here is an area, looking again at the FEMA viewer, and we zoom in, and we don't have a lot of detail in there's portions that are still part of the 1D, and we've got our floodway and we've got our normal cross sections. But in some of these breakout areas, we don't have a lot of information. And we've got some situations here where we've got these little islands of zone AE, they're detailed study areas. So in those cases, one of the questions, well, and we do have an elevation in each of those that we can use, and that is the most detailed we've got in those spots. So we can use that as a BFE, and then we're looking at, well, gee, do I have to consider this floodway or not? And if they are these little islands, we can consider them flood fringe and allow filling in those areas and use those elevations that are on the map. So it's not so bad for that area. Oh, there's another spot there. But then we're looking at another area in Duluth here and in Tisher Creek area. Here's the main stream going around, and we do have the detailed study, the 1D model that comes through a portion here. We've got a zone A 1D model continuing over here, but this area, we have the breakout flow, and we've got a lot of 2D modeling. And I'm going to look at a couple different sites and show some examples of how we'd figure out the BFE there. So this first site here, if we look on our lake and flood elevations online, this will show us the information along that 1D portion of the stream that is zone A. Basically, this is showing the area where we've got that 2D modeling, we've got that mesh that is the 2D modeling, and there's all these little cells, 10 foot by 10 foot squares that are the cells there. And the blue line over here shows the edge between the 2D and the 1D. So anything that was falling on the other side of this blue line went into that 1D model, that A zone model that we've got. And the rest of this is that 2D information. Okay, here I'm getting at my first example, and I picked a school, a middle school, public building, nice example there to use. And you can see there's all these contours. This is a steep area. Those of us in Minnesota know that there's very steep parts in Duluth. So here's what the building looks like. It's a big building. And one thing I want to mention is that the one issue with the model is that it doesn't just obstruct that area where the building is. So obviously the water wouldn't be going through the building. So that's something that in more recent modeling, they would have looked at a way to show that that area doesn't have flow going through it, because that is a big building. And then we look at what elevations we have in the area, and they don't go in nice 1 foot increments or 2 foot increments. Here we've got 855, we've got 876, 864, 891. They're all over the place. And here I've got some of those elevations that were near the school and on top of the school. So if I'm trying to figure out what the BFE is, that's a really tough call at this site. Looking at the National Flood Hazard Viewer, the FEMA viewer, it doesn't really help us. And then sometimes we'll look at the FEMA map panel and it'll have more information. But in this example, that FEMA map panel is even worse than what we were seeing in the viewers. It's not helpful at all. So I had Madison Rogers, one of my mapping co-workers, help me out with getting the modeling. And this shows that mesh that we were talking about, that 2D mesh, that the 10 foot by 10 foot squares that you'll see in all this area here. And the little bit darker area shows the FEMA mapped areas, what's on the FEMA map. And then we bring in another layer where we can set it to the max elevation, what the 1% elevation is in each of these squares, and click around in the squares, hover over those squares and see what is the elevation here. So Madison helped me out and hovered around the building here and found that the highest of the BFEs on the building was this 884.8. 884 point here was that highest cell elevation. So that's what we'll use as our base flood elevation based on this 2D modeling. And again, that's much more accurate than trying to use those numbers that were here on the FEMA map. So I wanted to look at another example. I wanted to look at a situation that we see pretty often, where the floodplain's just kind of nicking a building. It might be a little hard to see on the screen, but here's a house, and it's got a little bit of the floodplain just nicking that. And I asked the staff who does LOMAs and LOMA-RFs, the letters of map amendments, letters of map revisions based on fill, how do you deal with these 2D model areas? And here we've got 730 as a BFE and 745. I've got a 15-foot drop through this reach. And what is it at this site? And the MT1 staff said they would prorate it. So I thought, okay, when I heard that, I thought that makes sense. I can see why they would do that. But then I decided to try doing the prorating on this site. And in our lake and flood elevations online viewer, we do have a measuring tool. So I measured the distance between the 730 and the 745, and that's this about 300 here. And then I measured just the distance from the 730 and did my math and determined that based on prorating, the elevation at the home would be 736.9. The BFE at the house would be 736.9. So taking that prorated distance, the elevation there, and adding it to my 730 there. And if you're working with this and need help, that's something you can be reaching out to those of us in the floodplain program to make sure you're understanding the math you need to do. But then I thought, well, let's look at what the contours show. And our alveol contours don't get, when I zoom in more, they're not as clear. I did use the county viewer here. And here's that same site. And there's the 734 contour, which is basically where the boundary of the floodplain is. So based on the contour, I would have estimated that BFE at 734, almost 3 feet lower than what it would be based on prorating. So I'm not too excited about prorating in this example because it really shows what I think is going to be too high of a BFE. And so then Madison helped me with looking at what that 2D modeling is showing. So again, we've got the mesh, and here we've got the darker outline of what is shown as the FEMA floodplain. And so we're looking at that area, and then again, bringing on that layer so we can click around and see what the base flood elevations are in each of the mesh cells. And so there's 2 cells that hit this building or that overlap with that building. So one's here at 732.79, the other's at 733.48. So we'll take the higher of those, and we'll say that our BFE is 733.5, because we'll round it to the nearest tenth, which is more accurate and lower than the numbers that we were getting, again, almost 737 using prorating, and the contour was at 734. So the contour wasn't too bad. That was at least close. So one of the things that we're realizing is that, especially in areas like Duluth and in areas where you really want to be looking at the model and at those cells to get a better idea of the BFE, we're going to be wanting to offer some training on how to open these up and look at these models. You don't need special licenses to be able to look at these. And I think that's the end here for this session. So then we're going to turn it back to Jeff, who's going to talk on about our next topic.
So we wanted to talk about the 2D models in that first session because some 2D regulatory models around the state, and basically more is coming. And at some point in the nearest future, FEMA is only going to want new maps to be based on 2D models. They haven't set a time when that's going to be true yet, but it's going to come in the future. And so that's why we want to do that first session. Well, the next big thing on the horizon is also already there, and that's something that they've been calling future of flood risk data. FEMA has been talking about this for a couple of years, and so this presentation is going to try to give a real high-level overview about what that is going to look like, and try to answer a few questions for you, because you may start hearing about this within the next year or two if you haven't heard about it already. The main point of trying to move to this future of flood risk data is to try to get away from binary analysis to a probabilistic analysis. So in the top of the screen here, you can kind of see, this home has an X on it because it's inside the mapped floodplain, whereas this home is out. Outside of that binary in or out line, showing that it's being good, so that's in a good spot. But the elevation difference between these two homes may not be more than a few tenths of a foot. So really, their risk isn't appreciably different if it's only a few tenths of a foot. But the way the binary system works out on the map, this person is forced to pay flood insurance, or maybe they're not allowed to build there at all, but this person is in good shape. And then they also want to be able to modernize data management and help drive more risk-informed decisions. And we'll get into that here. And I also want to point out that I borrowed heavily from a few different sources. Very few of the things in this presentation are things that I generated myself. I didn't cite each individual thing I borrowed, but these three references provide a lot of additional information. And if you go to any of them, particularly this middle one, you will see a lot of the same images that I borrowed for this presentation. For traditional FEMA map, this is kind of repeating myself a little bit. You see a floodway. You see this blue area being the 100-year floodplain, the orange-brown area being the 500-year floodplain. Again, it's binary. It tells you if you're in or out any of these spots, but it doesn't really give you a good idea what your risk is in any given spot. People just want to be on the right side of that line, so that way they don't have to pay flood insurance. But like I was trying to say before, they want to move to a more probabilistic approach. So the traditional approach, as we were talking about before, is these 1D models with cross sections going up the stream. Some streams may or may not be, some tributaries may or may not be mapped, and you're only getting information based on those streams that happen to be modeled. For the probabilistic approach, they want to look at the whole watershed. So you're getting additional tributaries coming in, even if doesn't become regulatory. And then you can also look at what they call fluvial and pluvial flooding. So the fluvial being flow coming in the river itself, and the pluvial being flooding that's happening, in the streets or kind of before it really gets into a channelized system. And it also accounts for additional probabilistic uncertainty. So on the bottom graph here, it shows precipitation versus your annual exceedance probability. So your chances here. So the 1% is usually what we're calling the 100-year storm. Well, that we're usually using that 50% probability, but really the confidence limits can be quite a bit higher and lower than that 50% probability. So trying to move to this probabilistic approach tries to account for that uncertainty and also look at a more watershed-wide approach. They're also able to add in future conditions as well. I wanted to make that point before I forgot it here too. So to illustrate this point a little bit more, this slide is showing a screenshot from an Atlas 14 table for precipitation for a particular site. And the zoom in on the right side, so the left side might be -4 font for some of you. So zooming in on the right side, you see in this particular spot, the 24-hour 100-year rainfall is 7.4 inches. But in reality, the confidence level is about 5.6 inches to 9.9 inches. A good analogy that I heard related to this is if you get on an elevator, often you're seeing something saying the load limit is 2,000 pounds. But I would feel a lot different about getting on that elevator if I had said load limit 2,000 pounds plus or minus 500 pounds. that changes things quite a bit. And if I'm on a crowded elevator and we're all, sucking in, holding our breath, trying to squeeze in, and I'm counting and getting 7, 8, 9, 10 people, like we're pushing that 2,000 pounds, and I'm not feeling super confident in that elevator at that point, because if we're hitting the under on that load limit, that could be bad news. But this is how we, for better or worse, this is often how we do this. We just take that 50th percentile and run with it, and kind of ignore that confidence level in many situations. And the same thing happens with estimating flows. This is a screenshot from StreamStats, which is using the USGS regression equations to estimate flows. Again, we might estimate it's about 5,000 CFS, but really it might be plus or minus almost 50%. And so the right circle is showing the standard error, so we're almost 50%. So in this situation, we might be modeling and mapping based on about 5,000 CFS, but the real 100-year flow might be, another 1,000 or 2,000 CFS more than that if you're using that 50% error. So that could mean a difference of whether or not somebody is mapped in or out of that binary situation. And another way the future flood risk data will incorporate some probabilistic is they'll be running Monte Carlo simulations running a storm track across a watershed. So this is a screenshot of lots of the Huck 10 watersheds across the metro area. And if you follow my mouse here, if you pick any given watershed, let's pick Minnehaha Creek for this example. If we get that 100-year rainfall, let's say we hit exactly 7.4 inches for that 100-year rainfall, whether that 7.4 inches is not going to cover the whole watershed equally. If it covered the whole watershed equally, we would get a really, the falls would be just roaring at the bottom of Minnehaha Creek. But it also would be, usually might get that 7.4 might be, a localized area in one spot or the other, but the rest of the watershed might get a rainfall that's at least a couple inches lower than that, if not more. And then it also really matters how that storm cuts across the watershed. If that storm cuts across Minnehaha Creek going straight west-east, going straight down the creek, that's going to have a very different outcome than if the storm is kind of going counter to what it usually does, but if it starts on the downstream end and starts moving upstream. So when they're doing this future flood risk data modeling, they do Monte Carlo simulations running storm tracks on lots of different ways across the watershed. And then they're taking kind of the worst case scenario in any given spot and then mapping the probability based on the results from that Monte Carlo simulation. That way it's a lot more accurate about what your real risk is at any given location. So again, this is screenshots from those slides. Kind of getting a little bit of repeat here, but again, shift from binary to probabilistic analysis. They want to modernize the data management and delivery. There's a lot more data that can be provided. It empowers private and other stakeholders and really drives that risk-informed decision. So if you really understand what your probability at a given spot is, it helps you understand, is it okay to cite a police station or a hospital or a school at one spot versus something else that might be a little bit more tolerable for a little more risk. So this kind of summarizes a lot of the inputs that come into this. They are plugging the rainfall into it. They're using terrain. They're using LiDAR terrain. You can put in lots of different things. You can put in reservoirs to help simulate how real life things on the ground would be impacting the results from these models. And I think I said at the beginning, maybe it's on a later slide, but the Army Corps of Engineers is heavily involved in some of these in the development of this future flood risk data effort. So it's a FEMA initiative, but the Army Corps of Engineers is heavily involved in it as well. And then because you're having all these additional inputs, you also can get a lot of different outputs. I mean, the main thing we think about is that annual probability. Is it in a given spot? Is it a 1% chance of flooding, 2% chance, 0.1% chance flooding at any given spot? So you can really run that probability for the risk of flooding, but you can also look at your depth and velocity and understand, where is that big risk of erosion or other things happening. You can look at just velocity, you can look at just depth, you can look at all kinds of different scenarios, outputs from this approach to modeling. So it's really exciting, and it's exciting when it's going to be coming out. It's going to really help drive decisions at the local and regional level. This is the same slide I was showing on the previous presentation. Again, just kind of illustrating that difference between only having results along the main stem of the river, but nothing mapped on the tributaries, and then showing all the additional flooding that you can, all the additional information you get on tributaries and pluvial flooding in the watershed as well. Here's where I mentioned that the Corps of Engineers is a key partner. So we see that that they're heavily involved in developing and testing this approach. So there are some questions about the exact timing when this is going to be rolled out. I said at the beginning that they've been talking about this for a couple of years. And I haven't seen any specific news about when they're going to be rolling this out. But it is something that we expect to start seeing, at least in some parts of the country, within, I would guess, within the next couple of years. I don't think they'll roll it out nationwide at first, but they will start rolling it out in some areas, and so it'll make it here soon enough, and it'll be exciting, I think, anyway.
So thanks for attending again today, and appreciate the interest, and we'll see you